For all our dreams of Mars, we're still bound to Earth by a stubborn law, the rocket equation. It's simple but brutal. Go faster, need more fuel, but more fuel means more weight, which means even more fuel. This cycle of diminishing returns has defined the space age. Our rockets are controlled explosions, burning chemical propellants for a brief, powerful push, like throwing a baseball hard, but it only gets one shove. After launch, spacecraft coast for months, following gravity's path. That's why a trip to Mars takes 7 to 9 months. We're forced to use a fuel-saving path called a Hohmann transfer orbit, waiting for the planets to align, a window that opens only every 26 months. Miss it, and you wait over 2 years for the next shot. Chemical rockets are powerful, but not fast enough to truly open the solar system. Months-long voyages make a bustling spacefaring civilization impossible. The dream of people and goods moving freely between worlds remains just that, a dream. To break the chains of the rocket equation, we need more than bigger rockets. We need a new kind of fire. The rocket equation isn't just a math problem, it's the wall we must break through. The future of space travel depends on finding a way around it. Only then can we truly reach for the stars. A 9-month journey to Mars isn't just slow, it's dangerous. Space is hostile to human life. Our bodies evolved for Earth's gravity and protection. In deep space, cosmic radiation bombards astronauts, raising cancer risks and threatening the nervous system. Earth's magnetic field shields us, but between planets there's no protection. Weightlessness weakens muscles and bones, even with daily exercise. Astronauts return from the ISS needing time to recover. A Mars trip would push human endurance to the limit. Then, there's the psychological toll: months in a cramped capsule, staring at the endless void, far from home. Isolation, stress, and conflict are real dangers. The best solution? Make the trip shorter. Cutting travel time from 9 months to 1 or 2 would slash radiation exposure, bone loss, and mental strain. Faster journeys mean safer missions. The rocket equation isn't just a technical hurdle, it's a health risk. To survive and thrive in space, we need to go faster. The future of exploration depends on it. What if Mars was just a month away? What if our ships could accelerate halfway there, then decelerate the rest? This is the promise of nuclear fusion, the same process that powers the stars. Fusion means fusing light atoms, like hydrogen, into heavier ones, releasing immense energy. It's the engine of the cosmos, and it could be the engine of our future. Fusion rockets would have a specific impulse, hundreds or thousands of times greater than chemical rockets. That means weeks or months of continuous thrust, not just minutes. With fusion, we're no longer stuck waiting for rare launch windows. Mars in a month, Jupiter in under a year. Suddenly the solar system is open. This isn't just an upgrade, it's a revolution. Fusion propulsion is the key to becoming a true multiplanetary species. The age of coasting is over. The age of continuous exploration is about to begin. To see how big a leap fusion is, let's compare our options. Chemical rockets, our current workhorses, burn fuel for a short, powerful burst, like a drag racer. Nuclear fission rockets, like nuclear thermal rockets, use a reactor to superheat hydrogen, doubling efficiency over chemical rockets. But fusion is a different league. Fusion rockets use the reaction's superheated plasma as exhaust, channeled by magnetic fields at incredible speeds. Exhaust velocities are tens or hundreds of times faster than chemical rockets. Higher exhaust velocity means less fuel for more push. Chemical rockets are like throwing a baseball. Fission rockets are like a pitching machine. Fusion rockets, a jet of sand, each grain moving at a fraction of light speed. Continuous thrust means constant acceleration, true freedom to move between worlds. Fusion isn't just a better engine, it's the difference between being a tourist and a resident of the solar system. It's the technology that will make the solar system our neighborhood. Fusion power isn't new, but building a compact fusion engine for space is a monumental challenge. To fuse atoms, we need star-like temperatures, hundreds of millions of degrees. No material can touch that plasma, so we use magnetic fields to contain it. A magnetic bottle. Companies, like Pulsar Fusion and Princeton satellite systems, are racing to perfect this. The direct fusion drive channels charge particles directly for thrust and electricity. The hurdles are immense, stable magnetic fields, radiation-resistant materials, and compact, reliable systems. But these are the frontiers of engineering. The people solving these problems are building the ships of the next great age. Taming a star is our ticket to the planets. Nuclear means different things in space travel. Fission splits heavy atoms, releasing energy but also long-lived radioactive waste and meltdown risks. Fusion joins light atoms like deuterium and helium-3, producing mostly harmless helium and little waste. Fusion is inherently safer, no meltdown, no runaway reaction, and only a few grams of fuel at a time. If containment fails, the reaction stops instantly. Fission rockets like Draco are a vital step, doubling efficiency over chemical rockets. But fusion is the clean, green endgame. No radioactive trail, no greenhouse gases. Fusion lets us explore responsibly, mimicking the engines of the stars. The future of propulsion is not just powerful, it's sustainable. To truly open the solar system, fusion is the destination. It's the ultimate power for a spacefaring civilization. The best fusion fuel? Deuterium and helium-3. Helium-3 is rare on Earth, but the moon's soil is rich with it, soaked up from the solar wind. The moon could become our cosmic gas station, fueling a spacefaring economy for centuries. Imagine robotic miners extracting helium-3, storing it at lunar depots. Spacecraft could launch from Earth, refuel on the moon, and then speed to Mars or beyond. This breaks our reliance on Earth for fuel. The moon becomes not just a destination, but the first outpost of a self-sustaining human presence in space. Lunar resources are the key to our expansion into the solar system. The path to fusion propulsion is unfolding now. First, fission rockets like Draco will double our efficiency and prove nuclear propulsion in space. Meanwhile, fusion research on Earth is accelerating, with breakthroughs in magnets and plasma physics. Lessons from terrestrial fusion will shape compact space engines. By the 2040s, we could see ground-based fusion drive prototypes. The first fusion-powered spacecraft might fly in the 2050s, reaching Neptune in years, not decades. As the tech matures, crewed missions to Mars in 30 days become possible. The journey is long, but the destination, routine, rapid exploration of the solar system, is within reach. For most of history, oceans were barriers, until ships turned them into highways. Now, interplanetary space is our new ocean, vast and daunting. Fusion rockets are the ships that will let us cross it. Mars in a month, Europa in a year, asteroid mining, these become routine. Fusion propulsion doesn't just make current dreams faster, it unlocks new ones. With continuous acceleration, even the nearest stars come within reach. Alpha Centauri, once a 70,000-year journey, could be reached in under a century. The night sky becomes a map of future destinations. The work happening today is forging the engines of our future. The cosmos is calling, and soon, we'll have the power to answer. The next great ocean awaits. The invitation is written in the laws of physics. The stars are not out of reach. Our journey is just beginning.